Today we'll talk about acid-base indicators and acid-base reactions. So acid-base indicators are compounds whose colors are sensitive to pH. Indicators change colors because they are either weak acids or weak bases. In our equation, HIN will go in the forward and the reverse direction, will produce H plus IN minus. So HIN and IN minus are different colors. In acidic solutions, most of the indicator is HIN. In basic solutions, most of the indicator is IN minus. So the pH range over which an indicator changes color is called this transition interval. Indicators that change color at pH lower than 7 are stronger acids than those other types of indicators. They tend to ionize more than others. Indicators that undergo transition in higher pH ranges are weaker acids because we know our stronger acids usually around, this was 0, 1, 2, 3, and we'll say 3.5. And if as they go up to get to 7 neutral, they're weaker acids. So another way to measure pH, the pH meter, determines the pH of a solution by measuring the voltage between the two electrodes that are placed in the solution. The voltage changes as the hydronium ion concentration in the solution changes. And we know from doing pH calculations, the hydronium ion, H3O+. And it measures pH more precisely than indicators. So these next few slides are just some color ranges of indicators. So if we have a titration type, we have strong acid, strong base. And if our indicators are methyl red or bromothymol blue, it shows us the color the indicator will turn at a designated pH. We'll also do this for a strong acid and a weak base, and the indicators are methyl orange and bromphenyl blue. And this should be bromothymol blue right here. And these numbers in parentheses are pH values. And then if we had a weak acid and a strong base, we have phenolphthalein and then phenyl red. So now, neutralization. So the term neutralization is used to describe both the reaction and the point at which a neutralization reaction is complete. So this picture, we see the hydronium ions, water molecules, chloride ions, sodium cations, and hydroxide anions. And it shows us in beakers, in solution. And then we have an evaporation. We see some white powdery substance, right? So this is the general form of a neutralization reaction, which we've already done before this year, but now we're going to get the specific, put these type of equations with a specific name. So neutralization reaction. Your reactants are acid, could be any acid, any base, and your products are going to be a salt. Now that salt it's not just going to be table salt. It could be another salt. Right here is our salt here. And our other product, this is never going to change, is always going to be water. So a neutralization reaction, we have an acid plus base will produce a salt and water. So, finding the moles needed for neutralization. So it says how many moles of sulfuric acid are required to neutralize 0.50 moles of sodium hydroxide. So we're at 0.50 moles of NaOH. We want to go to moles of H2SO4, so just a mole-to-mole stoichiometric calculation. So we have 1 mole of H2SO4 all over 2 moles of NaOH. So we plug that in your calculator, and we get 0.25 moles of sulfuric acid. So now, the next step after neutralization is titration. So once again, neutralization occurs when hydronium ions and hydroxide ions are supplied in equal numbers by reactants. So H3O plus OH minus will produce H2O. And titration is the controlled addition and measurement of the amount of a solution of known concentration required to react completely with a measured amount of a solution of unknown concentration. Okay, so now the steps in an acid-base titration are as follows. Number 1, a measured volume of an acid solution of unknown concentration is added to a flask. Number 2, several drops of an indicator are added to the solution while the flask is gently swirled. And number 3, measured volumes of a base of known concentrations are mixed into the acid until the indicator just barely changes color. So this first flask, a flask with a known volume of acids and an indicator, is placed beneath a burette that is filled with a base of known concentration. So the base is slowly added from the burette to the acid, and a change in the color of the solution is the signal that neutralization has occurred. So the solution of known concentration is the standard solution. You can use a similar procedure to find the concentration of a base using a standard acid. Once again, neutralization occurs when the number of moles of hydrogen ions equal the number of moles of hydroxide ions. So H plus is equal to OH minus. Remember, these are the number of moles. We could also have H3O plus here instead of the H plus. Okay, and the point at which neutralization occurs is called the equivalence point. So, equivalence point. Indicators that undergo a transition at about pH 7 are used to determine the equivalence point of a strong acid-base titration. The neutralization of strong acids with strong bases produces a salt solution with a pH of 7. Indicators that change color at pH lower than 7 are used to determine the equivalence point of strong acid, weak base titrations. The equivalence point of a strong acid, weak base titration is acidic. So, the indicator that is chosen for a titration must change color at or near the pH of the equivalence point. The pH at which the indicator changes color is the endpoint of the titration. So, this graph shows the pH of a solution changes, so how the pH of a solution changes during the titration of a strong acid, HCl, with a strong base, NaOH. And we see here that the initial pH is around 1. It's in between 0 and 2. And as NaOH is added, the pH increases because some of the acid reacts with the base. So the equivalence point for this reaction occurs at 7, which it shows here. And as the titration nears the equivalence point, the pH rises dramatically because hydrogen ions are being used up. So extending the titration beyond the point of neutralization produces a further increase of pH. And if we're going to go past a pH of 7, we know we now have a basic solution. So if the titration of HCl and NaOH could be stopped right at the equivalence point, the solution in the beaker would consist of only H2O and NaCl, plus a small amount of indicator. Because we know in a neutralization reaction, our equation, so our acid is HCl, and our base is NaOH. So, at the equivalence point, 7, all we would have left over is our salt, NaCl, and our water, H2O, and some other indicator. Okay. This graph shows titration curve for a weak acid and a strong base. We see the pH is a little higher here. It's around probably 2.75, and the equivalence point's a little higher as well. It's around 9. Okay, so performing a titration part 1. So the following procedure is used to determine the unknown concentration of an acid solution by titrating the solution with a standardized base solution. Decide which burette will be used for the acid and which will be used for the base. Label each burette to avoid confusion. Rinse the acid burette 3 times with acid to be used in the titration. Use the base solution to rinse the other burette in a similar manner. Second step, we're going to fill the acid burette with acid solution to a point above 0 milliliter mark. Number 3, release some acid into a waste flask to lower the volume into the calibrated portion of the burette. Number 4, we're going to record the volume of the acid in the burette to the nearest 0.01 milliliter as your starting point. Number 5, release a volume of acid determined by your lab procedure into a clean Erlenmeyer flask. Number 6, record the new volume reading and subtract the starting volume to find the volume of the acid added. Number 7, add 3 drops of appropriate indicator, phenolphthalein in this case, to the flask. Part 2, in step number 8, fill the other burette with the standardized base solution to a point above 0 milliliter mark. Record the concentration of the standardized solution. Number 9, release some of the base from the burette into a waste flask so that the top of the liquid is in the calibrated portion of the burette. And number 10, record the volume of the base to the nearest 0.01 milliliter as your starting point. And number 11, place the flask containing the acid under the base burette. Notice that the tip of the burette extends into the mouth of the flask. And number 12, slowly release the base from the burette into the flask while constantly swirling the flask. The pink color should fade with swirling. Number 13, near the end point, add base drop by drop. The end point is reached when a very light pink color remains after 30 seconds of swirling. And number 15, record the new volume and determine the volume of base added. Okay, so molarity and titration. So the key things with doing calculations like these, we need to start with the balanced chemical equation for the neutralization reaction and determine the chemically equivalent amounts of acid and base. Number 2, determine moles of acid or base from the known solution used during the titration. Number 3, determine the moles of solute of the unknown solution used during the titration. Number 4, determine the molarity of the unknown solution. Okay, so example here, it says in a titration, it says 27.4 milliliters of a 0.0154 molar BaOH is added to a 20 milliliter sample of HCl of unknown concentration until the equivalence point is reached. What is the molarity of the acid solution? Okay, so now what we need to do is we need to create our neutralization reaction. So we know we're going to have a salt, so in this case it's going to be Ba and Cl2 plus water. Now, we need to balance this. So let's try to put a 2 in front of HCl and a 2 in front of H2O. Let's see what we have here. So we have one barium. We have on this side now, we have 2 oxygens, and we have 2 oxygens on this side, so we're good. Hydrogens, we have 4 on the reactant side and 4 on the product side, so we're good. And then chlorines, 2 chlorines on the reactant side and 2 chlorines on the product side, so we are good. Okay, so now we have 27.4 milliliters of a .0154 molar solution. And now we have a 20 milliliter HCl, but we want to know the molarity. Seems like what we did last unit with solution stoichiometry. So we have 27.4 milliliters of BaOH. We want to change those to liters. So 0.001 liters of BaOH all over 1 milliliter of BaOH. Okay, so now we're going to use our molarity. And we have 0.0154 moles BaOH all over OH2, sorry, over 1 liter of BaOH. Let's extend here, put it down here. So now we're in moles of BaOH2. We want to get to moles of HCl. So we're going to use 2 moles HCl all over 1 mole of BaOH2. All right, so now erase this here. So I'm going to stop our dimensional analysis right here. What I'm going to calculate my mole value for HCl. So I have 27.4 times 0.001 times 0.0154 times 2. We get 8.43. So we'll round that up. Okay. So we'll say 8.44 times 10 to the negative 4th moles. Okay, so now we know our volume. We have 20 milliliters. You change those to liters. So our molarity would be .04 molar. Okay, so now one more example here. And it says, a 25 milliliter solution of sulfuric acid is neutralized by 18 milliliters of 1 molar NaOH solution. What is the concentration or molarity of H2SO4 in the solution? And the equation is above. So we'll start with our 18 milliliters of NaOH. Change those 2 liters. Now, so we know 1 mole of NaOH all over 1 liter of NaOH. Since we're in moles of NaOH, we can now go to moles of H2SO4. So we know we have 1 mole of H2SO4 all over 2 moles of NaOH. And we should get 0.009 moles here. Okay, now we'll change those 25 milliliters to liters. So 0.009 divided by 0.025, we should get 0.36 molar. And the last thing in this video talk about acid rain. Oh, get this out of here. So, acid rain. So, nitrogen monoxide, nitrogen dioxide, carbon dioxide, sulfur dioxide, and sulfur trioxide gases from industrial processes can dissolve in atmospheric water to produce acidic solutions. So, in this case, we have sulfur trioxide plus water will produce sulfuric acid. So very acidic rain is called acid rain. And acid rain can erode statues and effective ecosystems, as we see here in this structure. Erosion from acid rain. And this concludes our video on acid-base indicators and reactions.